All right, hell yeah. So we got material mechanics. This is gear. This is a brief edition. So hell yeah, this is the but anyway, we're gonna go over torsion and we're gonna try to we did an overview. Oh bummer. It's really difficult to actually get on these pages. All right, sweet. Okay, so we did this introduction. So we kind of know what torque is, and we kind of know why things would deform when we torque on a cylinder. You know what I mean? They're going to twist. Okay, hell yeah. And hopefully we're going to get into this derivation because I think this gets a little bit tricky. And then we have like this is the full. So this is this little section dx. Sometimes it's difficult to see. Like this is the whole shaft. And then we're going to take a little section right here. And even in this section, we're even going to take a smaller section that could be anywhere. That could be a very tiny cylinder, or it could be all the way out to the full radius. And so that's what that picture is. Okay, hell yeah. So let's read our way through. So we have, and we can even get a lot closer. Torsional deformations of a circular bar. We begin our discussion of torsion by considering a prismatic bar of circular cross-section twisted by torques T. Those are the torques. So T is the moment or the couple, and they're going to act at the ends. So we're going to see figure 338. Anytime you read text, it's very good to actually just go right to the figure and be like, okay, this is what we're talking about. Here's the torques. In the last video, they said, hey, you can use these double arrows. You put your thumb in that direction and then sweep your hands like you're waving, and then that would be a torque going this way. This would be a torque going that way. So you'd stick your thumb that way and then wave your fingers. So hell yeah. And both of those are going to be twisting the bar. Let's say this is fixed or welded to a wall, um, and we apply this torque. Well, it used to be right here at Q, and now this little section is down to Q prime. And that distance, this angle that gets generated, is a function of this length. If the length isn't very much, you know what I mean? This distance, Q to Q prime, isn't going to be very much. And now I'm bummed out because see how this Q to Q prime is represented as an angle? This angle actually remains the same. This angle is not a function of the length. The distance this travels, so like if you say like, hey, Q to Q prime, if you're interested in that, let's say you're like twisting this thing and you have a little nubbin sticking out, and as you twist it, it makes contact with something else. I mean, that could be a physical thing that could be useful. Well, it's going to move from Q to Q prime, and that's going to be a function of the radius and then this, you know, a portion of the circumference. But this angle, I think I misspoke. It doesn't matter if we take half the length. Look at this. Hey, that's the same. Is that the same angle? Doesn't look like the same angle. No, it is. So yes, this angle is a function of x. Sometimes that's why we're doing this, because reading textbooks is very difficult. You know what I mean? Because you just the second you get one thing in your head, you're just like, I think this is what's happening, and it's wrong. Man, that can really mess you up. But hell yeah! So this is the very end. This is what we're gonna see. We're gonna see this angle. But if we slice right here, look at this. It's a smaller little segment. And then if we slice right here, that's going to be a little sliver. So you're not going to have any angle change. So this angle is additive. I was just thinking how the molecule is sheared. We can talk about that. And we even have our writing tools. So we could even do something like that. All right, booyah. All right, so back to it. We're going to be, so we see that figure. Since every cross section of the bar is identical, and that's the thing, you know what I mean? What I'm envisioning is this. I'm always envision like, hey, there's a molecule, there's a molecule. I really need a pad. You know what I mean? But anyway, so and then we're going to have a full circle of molecules. So you have a disk of molecules, and then right next to it, I'm going to say like, hey, this is right next to it. We're going to have another disk of molecules. So we're going to have a ring of molecules around the perimeter of this cylinder, and then we're going to fill it in one layer deep. I mean, so there you go. So this thickness of those molecules are that thickness, this thickness, and we're just going to pretend that both of those thicknesses are just right next to each other. Hell yeah. And it's those interactions of those molecules. They can be just one molecular width thick. And so there you go. So there's the cylinder, cross section would be like 1, 2, 3, and then maybe, you know what I mean? There you go. So you have this cylinder, and those are what and let's spell it out, because I think it's very useful to imagine this is a very large cylinder, like very large, and gotta be careful of what we're drawing. And then you're gonna take a small little square, and what I do is just I do this. So I for the small little square, I'm just gonna put 4 elements, and guess what's gonna happen? Those elements, and then these are gonna be all the way around. You know what I mean? So there you go, there you go. Sorry, I didn't draw it very good. But anyway, so you're going to have another square there, and they're going to go all the way around. But it's the fact that, and then let's say I twist this. So I'm going to twist this way. Let's see the picture is going this way. So I'm going to twist this way with a torque, and then this way with a torque. Cool. Okay, that means that these molecules are going up. So I'm going to draw these two up, and then these molecules are going down. But if I apply this torque and I don't see a rotation, you know what I mean? Well, obviously this torque is this way and this torque is that way, and they're balanced. But the internal reactions have to, like if I take a slice right here through the middle, or I guess just however you do that. But yeah, so it's every line of molecules has to resist that torque, one on one face, one on the other. And so we're going to apply a force, just call it V for shear force, and a force this way. And that force is a distance away. See, it's a distance, the radius. That's going to be the distance away from the center. And the shear force on these molecules multiplied by this distance from the center is equal to the torque applied. If this cylinder is just one molecule of thickness of so yeah, you have a hollow cylinder, you know what I mean, with a thickness, a wall thickness of just one molecule. Then it's these molecules that are resisting that torque, and it's the shear of these molecules. And so, well, we have a shear force on those molecules, and then they're a distance away. So now we know that is the definition of a moment, or a couple, or I mean a torque. And so this torque generated, this shear times this distance, is balancing this torque at this end. Hell yeah. And let's say I just have like 100 of these little squares all the way around. Well, this is going to be this force is going to be 1/100th of the, so let's say, so we have torque. So this torque right here has to be balanced by this shear force, and we're just going to call it 100 times V times this distance R. And then this is a force, this is a distance, and this torque is a force and a distance. So our units are the same, and this is exactly what's happening. It's, whoops, so booyah. All right, hell yeah. I think we just need to start reading some more. But that's a good little overview. Not really. Just kidding. Anyway, since every cross-section of the bar is identical, And since every cross-section is subjected to the same internal torque, we say that the bar is in pure torsion. Yeah, there's no other, you know what I mean? So the diagram that I did of the square and the four little, you know what I mean? Those are the only things that's resisting that torsion. From consideration of symmetry, it can be proved that the cross sections of the bar do not change in shape as they rotate. Yeah, that's just kind of fascinating. There's a lot in material mechanics, there's a lot of things like that. That if you do one thing, it means, you know, I mean, symmetry. And so in this case, we have that. And it's just the way the molecules interact. And it's because we have a homogeneous, you have all the same molecules. It's a steel bar. Yeah. Anyway, and they do not change in shape as they rotate about the longitudinal axis. Therefore, if I have a disk of molecules right here and a disk of molecules right here, and this is the top, and this disk rotates where now those molecules are over there, they don't, I mean, they just purely rotate that new angle. So it used to be here and now it's there. Nothing, you know, this is still a perfect circular disk of molecules. This is still a perfect circular disk. They don't all bunch up on one end and then, you know, leave the other end. All right, booyah. Where are we at? So it says, in other words, all cross sections remain plane and circular. Yeah, cool. Yeah, that's why reading these textbooks, it's always good to stay one step ahead. Like I haven't prepped for this. I'm just reading a textbook and then knowing, you know, hopefully I know what it's going to say. Cool. And circular and all radii remain straight. Therefore, if the angle of rotation between one end of the bar and the other is small, so that's the other thing. A lot of these are just very small deformations, and the angle of rotation is what we're going to be considering a deformation. That's a shear deformation, because that square, you know, turned into a diamond. Furthermore, if the angle of rotation between one end of the bar and the other is small, neither the length of the bar nor its radius will change. Yeah, so that's kind of interesting. You would think that if you had a bar and then you twisted it, I don't know, maybe it all just bunches up. You know, if I have a spring and I go and twist it this way and twist it that way, well, it's going to get a tighter spring and the length is going to change. You know, so this isn't obvious, but it says if these deflections are small or the rotations are small, the length don't change, and the radius. Because even with yeah, what happens with a spring? You have a normal spring like this, and then you do this to it, like it's going to wow, this is not intuitive for me. But with a normal little spring like this, you could rotate it one way, you know, crunch it in or like extend it out. Anyway, you could apply a torque in both directions. So your arrows, double arrows, either that way or the opposite way. And two things are going to happen to a spring. It's either going to lengthen or shorten, and definitely the diameter is going to increase. It's going to get fatter or skinnier. And so that's the other thing. Physical properties, they're always going to be talking about the radius. I don't know. I think it's useful to talk about the diameter. You know what I mean? They could have said the diameter will remain. For this, they could have said the length of the bar won't change, nor will its diameter. And that would have made more sense to me. Saying the radius won't change, it feels like I got to do a mental push-up just to kind of understand what they're talking about. All right, booyah. Hell no. Well, we haven't even plugged in our, you know, like our microphones. This video just sounds awful. So let's do that. All right, hell yeah. So we got our microphone plugged in, thank goodness. And where are we at? So hell yeah, the length won't change, the diameter won't change. We talked about how the radius won't change. Okay, so to aid in visualizing the deformation, meaning the rotation of the bar from one end to the other, to visualize this, imagine that the left-hand end of the bar is fixed in position. And I already talked about that. You know, they should actually have a picture in this diagram, 3.3a, of it being welded to a wall. But anyway, you just have to just envision that it's fixed. We'll go back to our picture. So over here, again, like I said, like I already envisioned it, like that I have a wall right here, and then we just have a nice, you know, someone did some nice beaded welds. Hell yeah. So that's what we have. All right, booyah. Okay, so we're reading textbooks. And we're going to move it on. So that's fixed. Then, under the action of the torque on the right hand end, under the action of the torque T, the right hand end will rotate. And if we go, let's see, thumb in this direction, and, you know, can I draw a little, you know what I mean? So there, whoa. I don't know what happened, but there's my thumb, and then here's my fingers, and we got 4 of them, and this is what my hand would look like if my thumb is that way. And then so my fingers can't move backwards, you know what I mean? I got the joints, and so I got to sweep my fingers this way. So that is, anytime you see like a right hand, you know, I forget that word, where you're just like where it's a property that you're just like, you know, we chose to use the right hand rule to represent these arrows, thumb in this direction, fingers that way. So this is the direction of the torque. So we could represent the torque as a curved arrow like that, and we could put a T, or we do the double arrows that way, indicating that we're going to use the right hand rule, convention, thumb that direction, sweep our fingers. So that's the way it's going to rotate. And we talked about how this little chunk used to be at Q, and now it's at Q prime. So that's the other thing on this. I need to, there we go. So this point, if we have a little marker, you know what I mean? If we just say like, hey, before we apply this torque, in outer space, I'm going to put a little dot there. Or just put a little sticker, you know what I mean, color code that little section of the bar, and then we're going to apply the torque. That little dot is going to move to this Q prime. All right, hell yeah, and I'm sure it's going to talk about that. Get some water. So hell yeah, the right hand end will rotate with respect to the left hand end through a small angle, and that's, you gotta recognize this, that all the deformations in material mechanics, they're hella small. And when we're talking about torque, like a torque, shear, like shear takes these 4 molecules and let's say makes them, and we're going to do it in the classic, this would be, no, this isn't, that's actually negative. But anyway, so yeah, so this is positive shear. Positive shear is where you have a clockwise. So that's the other thing that we're going to bring up right now, because it sucks. You're just like, why is the convention different? Because this, if I say this torque or moment, T or M, you know what I mean? I'm going to sweep my fingers in this direction. My thumb is pointed out towards you. And that's going to indicate positive moment, positive torque. But when this type of shear, this is going to be positive shear. So what gives? Well, I'm not going to get into it, but it's because we're rotating this thing clockwise. Clockwise rotation is positive shear. Yep. And I think it's because of this. Like, let's say we have a bar and we do this and we turn it into a smiley face. Well, check it out. This portion of the bar did this. And then, so all throughout this bar, we are going to have, what would we have? Oh, I think we just need to move on. Sorry about that. But hell yeah, that'll be for another video. But it's because it's is because like this gets duplicated, one or the other gets duplicated, depending on if you're looking at the left side or the right side. Because here, if we're calling this, so this bar has a moment over here and a moment over here, and we're calling this positive. Well, this is a negative moment, thumb is going into the screen. This is a positive moment, thumb is coming out. But both of those in unison create a bending, smiley-faced beam that we are going to say that is a positive bending moment. So when we talk about bending moment. So yeah, so that's kind of part of it. I think I need to move on. That would be, I'm just going to get into a whole. All right, hell yeah. So let's read the next thing. Yeah, and that just shows where I need to improve upon. I can't just spit out why the convention. I mean, I know shear is clockwise, but I kind of forget why it gets duplicated and why we need. I don't know why it's useful. I think it comes down to when we do the graphs. Like, so if I have, this is my shear graph, and then this is my bending graph. Well, let's say I have, there's my shear all the way across because I have, a distribute. No. Sorry about that. I think I can erase one at a time. But let's say I have, this is good because if I have a beam or just a ruler and I apply a moment this way and then a moment over here. So this is a pure moment, and then the moment diagram is going to be constant. So any cut through here, take this little thing, is going to have a moment that way and a moment that way. And it's going to bend like this, and we're going to call that positive. And so here is what we indicate in the graph. And this graph means that if we take a slice, any slice out of this, then if this is the 0, and so we're going to read this positive number, it means that we're going to get positive moment. What's that? This little slice is going to look like a smiley face. So it's going to look like that. And to do that, on the right side, we're going to have a positive moment, and on the left side, we would have a negative moment, via the right-hand rule. And then from calculus, we would take the derivative of a constant, and that would just be 0. So we're just going to have 0 shear force. But if we do have a beam with a distributed load, where we have a constant, I don't even know how to do that one. But I think if we have a beam with a load in the middle, then that diagram I do know how to do. We're going to have positive there, positive, negative. And then when we do the bending moment, it's going to look like this. From calculus, we have a constant, integrate it, it's going to be a linear line. If we have a linear line and we take the, let's say this is just y is equal to x, when we take the derivative of this, we're going to get y is equal to 1. Cool. And this could be 2x and this could be 2. Hell yeah. And then similarly here. Okay, is this going to help us explain? So in this, hey, our moment is always positive, and then so every little slice is going to be like a smiley face. Hell yeah, positive moment. But our shear is going to be positive and then negative. And it's going to be right where we apply the load P. So if this is the load P, the ends are going to be P divided by 2. I still don't think I'm going to get there, and I just apologize for this tangent. But hell yeah. So if we take this little slice right there, we're going to have P divided by 2 this way. So P divided by 2. And look where this force is. And then on the cut, yeah, I think we're there now. So on this cut, so we're going to take, so this is the little beam, and we're going to take this little cut right here. On this face can be the only place that can, balance Newton's laws. You know what I mean? So if I have an upward force, I have to have a downward force that's equal. That's going to be P divided by 2. And look at these forces. They're causing this thing to rotate in a clockwise motion. Hell yeah. So that's going to be positive. We're going to say that's going to be positive. Where if we go over to this side of the bar, just going to cut right there, and then we have this little section, we're going to have a P divided by 2 up. And that means on this cut face, we're going to have a P divided by 2 down. Look at this. It's going to cause it to rotate counterclockwise. And then so that's going to be a negative shear. But why did we... so let's just experiment. What if I called this a positive shear? Okay, because this, look at this. If we use the right hand rule, my thumb is sticking out of the page, my fingers are rotating in that direction. Cool. That means that we have to take this graph and do this. And so finally this explains it. Because these two are mathematically accurate. You know what I mean? If this is the area under the curve, I have positive area, bigger positive area. That's not how it works. Sorry about that. It's opposite. You have to look at this. This would be the slope. See this slope? Hey, it's a constant. You know what I mean? You have, if this is the, does that make sense from calculus? Like if I'm going from this graph to this graph, I take the slope of this to get this. If I'm going the other way, if I have a constant line and I want to integrate, well, that's going to be linear. And then if I integrate again, and this is a constant, and this is a line, the area under this curve is going to be parabolic. And because you're going to add up this area, hey, no area, and then whatever the area you're adding from here to here is going to be this value. So like hardly any value. And then we're going to add just a little bit more area. Value gets bigger. And then we're going to add more area. So it's not going to be linear. If we added the same amount of area, we would have a linear line. But we're constantly going to be going above that linear line. So hell yeah. So any point on here, you could draw a tangent. You know what I mean? Because that's going to be the value. The area of under the curve right there is going to be this value. And you know, it makes the graph to there. And if you just continue that in a linear form, the next little slice that you add is going to be just a little bit bigger. You know what I mean? So now we're just above that. And so that's the kind of the definition of the square, x squared graph. Parabolic is what they say. Hell yeah. So yes, if I said this shear from the right-hand rule is positive, well, it makes the calculus not work out as nice, because then I would have this would be positive, this would be negative. So my moment is going to be negative and then positive, instead of positive then negative. And then here is my graph down here, and then I have a negative value for the moment. But still, this thing did not change shape, and then so I would have to say that if a beam bent like this in a smiley face, I have to call this negative. And it just makes sense to, if you have a beam in a smiley face, to call that positive moment. I don't know why. I mean, that's just a convention. It doesn't really matter. You could be like, smiley faces suck. They're messing up my day, and they're negative. You know what I mean? That doesn't make sense. But it really doesn't matter, because yeah, like literally, it's because we chose bending something in this way and calling that positive. That is where this shear has to be counterclockwise. So this is a counterclockwise, and that is negative. So counterclockwise, which would be positive with the right hand rule, is negative for shear. It's because if I have something that's kind of rotating that way, well, I think I'm done, because I'm just going to go in circles, and I'm sure there's a little bit more to it. But hell yeah, if you have a beam and you bend it like this side is rotating that way, this in shear is rotating that way, and we have to have a convention. But first we have to have a convention. This is positive moment. The graph will look like that. And then so the shear graph will be positive and then negative. So this over here we have to say is positive shear, and guess what? That rotates. That piece rotates counterclockwise. All right, that sucked, but we'll get better at that. That didn't seem like it seemed all right. Okay, booyah. All right, so back to that figure 3.3a. We're almost there. Not really. So through a small angle. So when we rotate that, it's going to rotate through that small angle. We talked about that. And that's where they just give these little terms. And I swear I don't pay enough attention, not to the letters. It's this little thing, you know what I mean? That this changes as a function of x. Like, this is a mathematical expression that I should be picking up on, and I'm not. I just say, look at this complex picture. It looks complex. I know that moved from there to there, and it shows me an angle. I don't know, it doesn't seem like they did a very good job, but I'm sure they explain it. But there you go. So next time when I'm reading more in this book, if I see something like this angle changes as a function of x. If it didn't change as a function of x, they would not, say, if something is constant, it's still a function of x, but it's just irrelevant. It's not changing. Cool. So therefore, it's probably not a function of x. I never know if something is a function of something else, even if it's like independent of that other thing. But this is dependent. This angle is dependent on the location of x. X is your independent variable. I can choose here, I can choose here, I can choose here, and then this angle is depending on where I choose. So I'm kind of getting better at that. And that is smart, just to be like, well, what is the independent variable? The thing that's just, and that comes back to mathematics, because, what we're saying, let's say it's time and velocity. Here's 1, 2 seconds, 3 seconds. Well, these are just, little, 3, 4. This is 1 inch, 2 inch, 3 inches, whatever, and then this angle could be anything. You know what I mean? So let's just say this is the length of this thing, and this is the angle. Here the angle is nothing, and here the angle is really big. Who knows what it could do? The angle might change like that. It might change linearly, which it does. It might change like this. It could do, I don't know. It could do a lot of different things, and so that helps me when something is a function of independent variable. So when I choose, this length right here, then I'm going to go measure that angle. And it's irrelevant to what the other location is. That's the whole idea of experimentation and observation is, sure, we can put a linear line after we observe a linear line, but when something's a function of the independent variable, that's what we're looking for. Is it just constant? You know what I mean? Is for whatever reason this angle just all the same? Like when I torque here and then move this, somehow magically, I don't know. Even though we welded it to the wall, it still just tears away, but magically reattaches. I have no idea. But hell yeah, so it can't be constant. You know what I mean? Because it's fixed to that wall. So it could be linear. But it doesn't have to be linear. It could be parabolic. It could be a lot of different things. Cool. So I think that helps me also process proofs and more complicated symbols. All right, booyah. All right, back to reading. How much? I'm about done, you know what I mean? But we're trying to get through this. Yeah, sorry for just... It's, I don't know. Like, I want to go at my own pace. I don't think it's wrong. I know that I, can only go about an hour, and then I'm just done anyway. So it's like, however far we got, that's how far we got. Some more water. But I do think it's very good reading textbooks when it says, hey, look at the figure. Go look at the figure. Cool. And then so that's going to rotate through that small angle. I'm going to say this right. It's phi. It's not phi. Phi. Just like pi is not... Yeah, I think you get it. I'm not going to steal that one from the viral math and physics geniuses of YouTube. But we'll get there. All right. So known as the angle of twist or angle of rotation. Because of this rotation, a straight... See, now I just spaced out, and I'm going to say when I'm spacing out. You know what I mean? Like right now, I'm not getting... Because I think I got embarrassed by saying another... Just by mentioning something about YouTube. Yeah, my brain is on crack. All right, so this phi is known as the angle of twist. I can buy that. It's also called the angle of rotation. I can buy that. And it's going to be a function of x. I'm so glad, because it's going to talk about that right here. Because of this rotation, a straight longitudinal line PQ on the surface of the bar will become a helical curve PQ prime. I did not know that. So let's go back to... So this curve is going to become a helix. And that makes sense. Like, unless this cylinder is just mondo-massive... and it's just hardly moving a molecule, you know what I mean, then this line is fairly straight. But, hey, let's say this rotates one full rotation. So that's the other thing about this. And we need to talk about this, because I mentioned with material mechanics, the deformations are small. And let's for sure talk about this, especially with shear, because what's going on the surface is we are getting shear. Oh, damn it. And shear is those four molecules, you know what I mean? And we're going to do positive as clockwise rotation, opposite of the counterclockwise right-hand roll. But hell yeah. So these molecules went to here. And what are I even talking about? Oh, yeah. So this, we're just going to go one step at a time. But this angle is pretty damn small. I think enough said. You know what I mean? The second we move this angle more, like all the molecules are going to rearrange, and then it's bent. Your tool's bent. Where if I pull down on this side and then pull up on this side, you know, let's just, even though I also have to, you know, push this way and this way at the same. These are all V, so that's good to know, because if I just push down and push up, this thing's just going to rotate. So I also need to go this way and that way. If you have a balloon, anyway, that's a separate video. But that's enough explanation on that. And what was I saying? Yeah, I guess you just you can only make a small deformation before doing that thing comes bent. Where if you push down this way, push up this way, and then do the equal, you know what I mean, so it doesn't rotate, and then stop these forces. You're going to apply these forces and then unapply them, however you say that. Guess what? This thing goes back perfectly to this perfect square. The molecules will always go back to their original location, 100%. But if you put too much force, well, you just permanently bent it. Now it looks like that. But up to that point, it's not permanently bent. And this is the kicker for material mechanics, is materials are hella strong in this magical range where you can apply a force, things move a little bit,
unapply that force, I don't know how to say that, but once you stop applying that force, the thing magically goes back to every molecule being in the same location in the universe that it was before applying the force. Apply the force, let go, it returns. Those locations are the same. And that's material mechanics at its finest. And you get a lot of strength. You can apply a lot of force to right before it bends. But guess what? It goes right back to this. But if you apply just a touch more force, guess what? It's going to be permanently bent. Now, if you bent it to here and then let go, you know what I mean? And it doesn't, it's going to go from here to a perfect square. But if you bend it just a little bit more, well, then does it just stay this shape? No. It goes back to a square-ish shape, but it now is bent. You know what I mean? So that's the deal there. But this is where all your strength comes from anyway. And the second you're starting to bend stuff, people might be losing their jobs and lives. And the lives are the most important thing. And so I always, even though there are things that you have to design portions of the system to go into that bent zone, and then other things are taking over. You know what I mean? Those are statically determinate. So there is that. But I don't think, well, that's the deal with material mechanics, is like you go from one complex topic to the other complex topic, and you lose the idea of just like, what are we trying to do? We're trying to make something strong and make sure people don't lose lives. Well, you know what I mean? This is where we can be in this linear range. And so when we do apply these forces, this diamond don't look like that. That diamond hardly looks like it moved at all. You know what I mean? So this angle is super tiny. If this was a meter by a meter by a meter square, this angle, so, keep this in mind. This is 1 meter or 1,000 millimeters. This distance right here, so if we do get an angle to take place, you know what I mean? Because this moved down. This distance right here, I didn't do a very good job, but hell yeah. So this is 1 meter, and we get this diamond shape to form. Let's say this is that 1,000. This distance right here is 4 millimeters. Very similar to steel when we have a meter of it, 1,000 millimeters. I can lengthen it 2 millimeters. And so why is this 4? I'm not going to go into that, but just know that, hell yeah, this is 2 millimeters. If I have 1,000 millimeter bar, 1 meter of bar of steel, I can lengthen it 2 millimeters. If I have a meter by meter sheet or thick plate of steel, I can reef on it that way, reef on it this way. I have to have these equal and opposite so it doesn't just spin. But there you go. Apply these shear forces all around. They're all equal in magnitude. And if I observe this angle to form, which has a arc length right here of 4, you know what I mean? You still got to figure out what the hell angle that is. 1,004. So it would be, this angle would be the inverse tangent of 4 divided by 1,000. But hell yeah. When that angle forms, that's the angle where if you do let go, it goes back every molecule in the same place. If you make more of an angle, it's going to be permanently bent. It's not going to stay this shape. It is going to return to a square, but this square is going to be square-ish, and you're going to have a bent square. You know what I mean? And it's going to be slightly diamond shaped. All right. So that show, and then what's the reason for that? And I think this is good. If I have 2 molecules of like iron, and I push up on this one, you know what I mean, do that shear force and push down on this one. Well, one is like, this is dumb because this thing is just going to rotate. If I apply this force and this force, if I have a little jet engine, you know what I mean, blasting off this way, and a little jet engine blasting off that way, the thing's just going to spin. And then the one thing is like this orientation, if it's here, and then I just move this one up, again, it just seems like they rotated. So that's the other thing with material mechanics. Is like we need four of them. Now the other thing though, if I do have two molecules of iron, let's say all the mass is like right there, mass is right there. We got these little electrons, little negatives, and we have molecular interaction, whether it's ionic, covalent, or if it's steel, it's just a sea of electrons. I think they call that a different term. But you got electricity, you know what I mean? You got charge holding this thing together. The question I have that I need to actually, after this video, go look up on AI is why the hell, when I pull axially on something, which I can pull quite a bit. Like if we're saying this is 1,000, you know what I mean? So we have two atoms of iron. It looks like my pencil ran out of juice. That was kind of funny. Anyway, I can move them to, you know, so whatever this distance is between the distance of two atoms of iron. I'm just going to say that's 1,000. Like obviously, who knows what the units would be, but it's 1,000. And I can move this atom two. I can move this one. Now it can be up here. And, you know what I mean? And this is the protons and neutrons, stuff like that. But that's significant still. Like a distance of 1,000 and move it 2? Like that ain't no pennies. And so the question I have is, like, I thought electrostatic forces dwindled by the distance squared. But maybe this is a large enough distance that it remains linear. I haven't done that. Like the one scenario I wanted to do was gravity, because it doesn't matter whether you're on sea level or on top of Everest. You're going to use G as about 9.8 or G as 10 would be just fine. You know what I mean? It's not going to change that much. But if you go to the International Space Station, hell yeah, gravity is not 10. And if you went halfway inside the Earth, that doesn't really make any sense. But hell yeah, if you go above the Earth, like even in an airplane, which is like 5 miles up, is it 5 or 7 miles up? I have no idea. It's 35,000 feet. Still not a big deal. So you're not. It's not a good weight loss plan just to like travel in the sky. You're gonna weigh the same. I have wanted to, next time I'm flying, I'm going to bring a digital scale, weigh myself on the tarmac, go up into that plane and weigh myself on the plane. For anyone, like any of the YouTubers, you should be doing that. That video should already be made, because you should have a noticeable difference. On a digital scale that's fairly accurate, it should be different. I thought from sea level to 35,000, from sea level to Everest, you're going to weigh 8 ounces. The average person is going to weigh 8 ounces less. Not even a pound lighter. But on a digital scale, you should be able to pick that up. But still, you got to do it you got to do it right before the plane is taking off. And then like the second you get up to 35,000. Just to make sure there's no hydration and dehydration involved in that experiment. But hell yeah. So because it doesn't change, because it's 9.8 here, it's 9.8 there, it's a constant value. And here's the deal. So if something dwindles with x squared, it's an exponential. You know what I mean? So just a parabola is, do they call this exponential? It's not an exponential. It's just x squared. But good enough, whatever. You know what I mean? It's not linear, that's for sure. Where what's happening here is that the value doesn't even change linearly. So that's kind of interesting. Holy hell! So let's so maybe I'm answering my own question. This is kind of fascinating. So if this is elevation, and I'm at sea level here, 35,000 here. Acceleration is here, and it's basically like this. It should be higher here and then just slightly lower. But you can't even tell. It's almost just a straight line. You wouldn't even be able to tell. If you could tell, you would probably register it as a linear line. Even though, if you could tell a lot, it's actually an x squared. Or, it's like an inverse squared or whatever. So actually it looks like this. Realistically, it looks linear. Just from a practical perspective, it's constant. So I think I'm answering my own question, because I thought I was going to use this example to further ask the question of like why, if this moves, these two atoms of steel move from 1,000 to 1,002 in distance away, like why is that a linear? Why is that linear? I should be asking, why is it, why does it even move? No, that'd be a dumb question. Yeah, anyway, so we have to get back, but anyway, so I think, I don't know. So that's one that I'm going to ask on AI, but it is a good one to ponder, because if I have a steel bar that's just represented as two steel, that's a bar, two iron atoms, Fe. Anyway, and I pull them apart, I can only pull them, and this distance is 1,000. I can only pull them 1,002 before they start to, and that's where you can, if you do have a steel bar, this is 30. I can increase the length of this by 30%, if it's a good specimen of steel, but it's going to bend after. If this is 1,000 millimeters, it's going to bend after I move it 1,002. But if I just move it 1,002 and let go, it's going to go right back to this original 1,000. But hell yeah! But that process it's a spring. It's linear. If I only move it 1 millimeter, well, it took a certain force to do that. I would have to double the force to move it 2 millimeters. Cool. If I apply a force on this bar and it only moves 1,000 meter bar and it only moves 0.5 millimeters, cool. I would have to double that force to make it move 1 millimeter, and then I would have to double that force to make it 2 millimeters. But at no point is it ever kind of this inverse square. So anyway, so that's for another video. But I do know that, and a good one to do is x squared. If you could probably do this on your calculator, you could take an x squared graph and then just zoom in anywhere. If you take a small little square box on your calculator right there, compared to right here, what you will get, right here you're going to get this. Here's your box, and you're going to get that line to form. That box right there on your calculator, you're going to get that line to form. Both look linear. So I think that's what's happening, and I just assume that it must be. That this distance, even though from a molecular scale, I thought 1,000 compared to 1,002 was astronomically huge distances when it came to the electrostatic forces. But even though it dwindles with x squared, and this is just x squared, but the inverse square, that's what electricity dwindles with. If I have a positive charge and a negative charge, and there is some sort of force, and let's say this is equilibrium, and I move them, and I move this one to right here. It takes some sort of force to do that. So I'm holding this one over here, tug of war. So I apply a force, and then I move, and this one's fixed. So I'm just holding this one. Move this charge to right here. It took a force to do that. If I'm going to move it twice the distance, it's going to take, and I should have done this in reverse. If this is in equilibrium, and I move this charge to over here, and let's say that requires a force to do so. just to hold it right there, far apart. It's like holding two magnets far apart. It doesn't take any force to hold them far apart. But then I move this one half the distance towards the equilibrium. Then it's going to take 4 times. It's going to take 4 times the force to hold it in this position. Than this position. But if I just move it from here to right there, if I move it from here to right there to right here, so I'm going to have 3 points. Let's say this is going to take 1,000 force. You know, whatever the units are, doesn't really matter. It takes 1,000 to hold it here. It takes 1,001 to hold it right here. Okay, and I'm going to move it, and that distance was just this much. I'm going to move it the same amount, that same little distance, and guess what? It takes 1,002. You know what I mean? So it's just kind of different with getting closer. 2 charges getting closer together requires more force to kind of hold them apart. But anyway, if it takes 1,000 whatevers to hold this charge over here and then this charge fixed right there, and then I move it just a small little distance d, and I register that it takes 1,001, I'm going to move that same distance d, and it should be 1,002. Because even though your graph might be doing something funky, you're zooming in, and you're just right here. And then, so like let's say that was, I'm right here at 1,000. I move, and this is the line that I'm on. This is 1,000, move it close, and sorry, it should be the other way, because it's the inverse squared. It should be like that. So let's get, so right there, this is 1,000. I'm going to move it that small distance, and I register 1,001. Move it a small distance, register 1,002. So that process is linear. Hell yeah. And honestly, that is kind of the aspect. That is the video that I kind of wanted to make. So I'm just glad I'm doing this. But I'm about out of gas. And like, but I don't think, yeah, this gets, yeah, let's just read until, let's just read until we get to about like right here. But I think kind of going through this, the whole reason I did that is just so then when you read the next sentence, you're not just going to lose your mind. Okay, so we have this idea that the rotation becomes helical, and I think we can agree with that. Fix this end, and I could rotate this one whole revolution. This line starts here, and then has to curl around, and then meet right back up. So that is the helical shape. All right, booyah. Oh man, have a hard time figuring out. So there, because of this rotation, a straight longitudinal line PQ on the surface of the bar will become a helical curve. And yeah, so you're starting, that's the other thing, it's just like you're starting with a straight line PQ and applying the torque, that straight line becomes the helical curve PQ prime. Cool. Where Q prime is the position of point Q after the end cross-section has rotated through the angle phi, after you apply the torque. The angle of twist changes along the angle of the bar. So that was the thing that I probably would overlook, and I'll probably still make the mistake of overlooking that in the future. And at intermediate cross-sections, it will have a value of phi of x. This is between 0 at the left-hand end and phi on the right-hand end. If every cross-section of the bar, so I know what they're going to talk about. They're going to say that's linear, right? If every cross-section of the bar has the same radius and is subjected to the same torque pure torsion, the angle phi of x will vary linearly. Hell yeah. Try to stay one step ahead of the textbooks is always a good idea between the ends. All right, so now we're going to consider shear strains at the outer surface. And we definitely talked about that with the little, we got the little molecules on the outer surface. And we went a step further of saying, hey, let's say this bar is actually a hollow, is kind of a hollow cylinder, where you have just a molecular thickness of iron molecules, so it's a steel bar, on the outer surface. So that was very useful. So now consider an element of the bar between two of these cross sections. And so that's going to be the next, between two cross sections. Let's reread this. Now consider an element of the bar between two cross sections, distance dx apart. I just don't like the way they wrote it. Anyway, so hell yeah. So this is figure. And then they said this was figure 3.4a. We have something to read right here. This is deformation of an element. The element is what we're cutting out right here. Of length dx. That's this length, just a small little derivative of length. I like to think of it, if we're going small, don't go too small. Make one molecule there and one molecule there. And then so you have a ring of molecules, So it'd be like that. Honestly, it would be like thin. And so you have a molecule there. That's the thickness dx. And then you have a lot of those molecules going around, and we have a hollow cylinder. So that's kind of what I'm envisioning. Hell yeah. So that length dx cut from the bar in torsion. Booyah. And that's figure 3.4a on the next page. This element is shown enlarged in figure 3.4b. So that's this one. Okay, so this is the cutout, and then this is the enlargement. Hell yeah. Now, what does it say about that? On its outer surface, we identify a small element, A, B, C, D. All right, so, and this is on the outer surface. So we have A, B, C, D. From a mathematical perspective, I pick up on this. It's just like, well, what was the rhyme and reason by labeling these? But they're starting at one point and they're going around a circle or a rectangle or a square to label these points. A, B, C, D. And that's good. Just because that's a lot of letters and that gets confusing fast, but hell yeah. So, and then when we rotate it, this straight line still becomes helical. So don't forget that, because this straight line looks straight, but just know that it's helical. But for all intents and purposes, what they're going to say is that this element is so close together that this helical line is actually a straight line. So AB prime is going to be straight. Hell yeah. And it should say that. So on the outer surface, we identify that small element ABCD with sides AB and CD that initially are parallel to the longitudinal axis. During twisting of the bar, the right-hand cross-section, see I'm spacing out, but so that right hand of the cross-section, so we have the cross-section, the right hand, and that's the other thing, is like, so perfect. So we have this cross-section, still, pretend like we welded this to the wall. Nice little beads. Booyah. You know what I mean? And so that'll be useful. Okay, so during twisting of the bar, the right hand cross-section rotates with respect to the left hand cross-section. But it's very useful to think of that left cross-section as fixed. That goes with the picture, makes it more intuitive. And that's going to rotate through a small angle of twist d phi. You know what I mean? So if we have and this angle is different. No, is it the same? What the hell? No. Oh, they're talking about d phi. Yeah. So this angle right here is d phi. Now, this d phi should just be phi of x, right? Unless I'm just losing my friggin' brain. But right here, this when this whole thing rotates. Oh, I guess not. This is fascinating. No, this is probably the trickiest part about this. So this face right here rotates that big angle. This face over here doesn't rotate at all. But one molecule over, so like this left face doesn't rotate. But if I take another disk right here and say these are all molecules, and I'm applying this torque, this disk does rotate. This used to be the tops of both disks. Now this disk is rotated a little bit. And so that is designated. And so we know that if I go out to this second disk of molecules, I'm going to have this angle form. But now what they're yeah. So yes. So let's take just to that very end. I think that's a good place to do it. Originally, those two disks on that very end look like this. You know what I mean? And they're in the same location. After rotating them, this disk is up, and then this disk gets rotated just slightly. So this used to be, if I drew that straight line right there, but now this straight line moves to there. And if I say, if I'm going to take this and then draw a rectangle on this, well, this is the original rectangle. This rectangle also moves right to there. This disk, again, did not have any. It's a phi of x at x is equal to 0. There is no angle. So this angle is 0. See, there's 0 angle. This angle does have some angle. So there you go. So because of that, this is going to be your, this is going to be phi of x, but this is phi of x. Oh, and this is good. This is, like, especially if I'm starting at here, this is x is equal to 0. Well, what is this? If I take my small little differential slice there, this is phi of x. This is phi at dx. You know, a distance dx. And then, and so this angle is the change. We went from 0 to the smallest change of angle possible. And so that's why calculus is very difficult as a language to talk your way through. But this is the change in that angle. This is the change in phi from here to there. And I hope I said that right. There's a chance that that was just totally awful. But this picture, so hell yeah. So there is no, so you just imagine this is that left face, that fully left face. This is one molecule over a distance of dx. And this one does have an angle formed. And that angle, instead of calling it phi of x, we're going to call it d phi. And the reason is because now, oh, bummer. Because now let's, it was very useful to take two cross sections over on that left side. But now we're going to take, just like they have, whoops, we're going to use this cross section. So right here at this cross section, what we know is, like, here's the original straight line. Here is the angle that gets formed. So this angle, and if we go, I don't want to go back up, but yeah, this is phi. This is the angle phi, and it's a phi of x. And so this angle right there would be phi at length L. You know what I mean? Phi at length L. Because these two slices are literally next to each other because of the differential, this angle, I mean this distance dx is just infinitesimally small, if not you know what I mean? So there you go. That these angles are the same. So even though the picture looks like, hey, it looks like that angle's bigger and this angle's smaller, I think this picture is misleading also, because let's say we use that Q. You know how we had like the straight line. Let's say the straight line is just right on top, and then this is still right here. Like this was right here. This was Q, and then this was Q prime. Q prime. Well, how about this? This is, let's call this QP, elemento Q. Let's call this O and O prime. You know what I mean? I should have used P, but anyway. So this is OQ. So this is Q. This is point Q, and we rotated to Q prime. This is point O, and we rotated to O prime. So same over here. This was the point Q that, and maybe I forget what they showed, but did they show this? This was Q, and this was Q prime. So we could do, yeah, let's redo this. But hell yeah! So we have a straight line all the way across, and then we have after. Oh, bummer, dude. Yeah, I definitely need a pad. But hell yeah! So we have this angle to form. This was Q. This was Q prime. How about we say this is P. This is P prime. QRP R. Oh. Elemento PQRS. Oh, I don't know why I was going. Anyway, I thought. Anyway, so QR. So this will be R. This will be R prime. RS. This is S, and this is S prime. But hell yeah. So this is the original point. This is the point it moved. Original point it moved. When they say this is A and B, I think this is your S prime. This is already, you know what I mean? And then this is R prime. But you still get, bummer. Yeah. So yeah, I think this will be a very good way to explain this. And this is probably the hardest part, like literally, because yeah. Let's go back up to that photo with the actual line on it. So right here, so we have this photo, and this is the rotation. Cool. Like, we know that this disk of molecules over here, I'm just going to designate it as this circle, and then I'm going to put this little thing right there as the original location. And then when I go over here, this was the original circle. It used to be right here, but now it's right here. Okay, hell yeah. And then same thing for right here. This little circle used to be right here, and now it's right here. But here's the wild thing that they don't really explain, is that if I take another circle that's like just right here, right next to it, a very tiny distance, a distance dx. This line used to be here. Now, is it the same? No, it's slightly more down. And so that's where, if this dx literally goes to 0, then these two disks are in the same location. So then if we do take this little dx slice and say it's so infinitesimally small that this is, the line used to be here, now it's down here. And then so the line used to be way up there. Now this thing got rotated way down here. But if these two slices are literally infinitesimally close to each other, this line is straight. I think that is good to, kind of like, okay, yeah. For all intensive purposes, these two disks are in the same alignment. But from physics, if this disk is different than this disk, and then we have another disk and another disk and another disk that make up this rod, there has to be a difference. Even though if you take this real small, yeah, these two disks are basically in the same location. That's what this line is. This is line Q. This is line Q prime at any cross section. So if I say this is Q and Q prime at this cross section, this is Q and Q prime at this cross section. They're right on top of each other. Now I'm cooking with butter. And then on this cross section, this is Q and Q prime. But you can see this is a hell of a distance, and even this is a hell of a distance. And we take this next slice, this is going to be Q and this is going to be Q prime. With a differential slice, these are literally in the same location, but there has to be a difference. So I think that's where now this line is angled, and now we have this change. We have this d, this derivative of phi, We know that at this point right here, this is phi of this is phi of x, and so right here this is phi of x, and then this angle is going to be phi of x plus dx. Because we are moving a small distance, this has to be a bigger number. And so that's what we're seeing. So hell yeah. Man, that is just hard to see, though, for me on my first go. So again, this line up here was that original equilibrium line. This is where this line represents where basically the two disks are like identical, they didn't really change, because this distance is so small. That line represents what I just talked about, how the disks are literally in the same location. This line represents, well, you know what I mean, this because this is phi right here, and they should have done this. This is phi of x. Yes, this book should be just a little bit better. And what they should have done is said that this angle right here, from here to here, is phi of x plus dx, which is the original phi of x. That angle right there is the same that's phi of x, plus this d of x. So this right here, phi of x plus dx, is phi of x plus some sort of change in that angle phi. Holy hell. Okay. The struggle is like, would I have to explain it the same way that I just did? You know what I mean? I think sometimes I fall into the trap of not quickly just being like, okay, no, I think we're there, but I should be able to explain that way faster next time. And because we have not only line AB, but we also have line DC, we took a small little rectangle. And so line DC, same thing, same as line AB. It's as if this gets so close together, yeah, these two disks are in the same location. They really didn't change from each other. But if we stack these disks one after another, there has to be a change, and that's what we're accounting for this change. And this is C prime. And the angle between C and C prime is that d theta. And booyah. All right. Hell yeah. And yeah, I think they could have done that picture from up here Like, how would have I done that picture? Drawn this d theta, or I mean, sorry, drawn this differential distance dx. Draw this line. I'd probably have to zoom in on that line. What I would do is draw that, say that this is that original line. Cool. And then draw this little rectangle. So we would have A, B, C, D. And then this is before torquing. It's right there. After torquing, this whole thing went from this line right there before torque to this line that's now slanted. It's helical. But because this distance is really close together, it appears, you know what I mean? So that's where this was the original. Oh, did I even do that right? Oh, I don't even know where. Oh yeah. So yeah, this is just the top. So this line right there is that original line, and then we're going to do this A B C D, and then we're going to torque this, and then this line is going to move considerably down here, and this rectangle is going to move right there. So this is our new rectangle. I mean, it just moves. So we have A, B, C, and C and D, but it doesn't look like a rectangle anymore. We have this angle to form, and so we get new locations for B prime and C prime, and this angle between B prime and B prime and C prime is that D phi. A little bit better. All right, that was brutal. All right, so hell yeah. So now what? So during twisting of the bar, the right-hand cross-section rotates with respect to the left-hand cross-section through a small angle of twist d phi. Yeah, and so that's interesting. Yeah, so all that, and they're just back to like just saying that sentence, and it's not so obvious. You know what I mean? They should say a differential slice might indicate that those slices are going to be right next to each other. But because those slices have to represent, you're going to have a series of differential slices throughout that cylinder, and you do have a change from one to the other, then each slice from one, even though you have a differential slice dx, the left hand and right hand face do rotate, and that angle is d phi. But they should also say that differential slice used to be in its original location after being torqued, like moved, like maybe 30 degrees. Maybe it rotated twice, because this is helical. This whole cylinder can, like this face, I can twist it once, twist it twice, twist it 3 times. So that's kind of fascinating. But yeah, so that little differential dx slice that we're making, that could also rotated twice. But that's not what we're trying to measure. We're trying to measure on one face of it, it rotated twice, and on the right side face, it rotated twice plus a little differential change in angle. So yeah, so that is kind of interesting. So that points B and C move to points B prime and C prime respectively. So the lengths, and hell yeah, I think we're done with that now. The lengths of the sides of the element, which is now element A, B prime, C prime, D, do not change during this small rotation. So they're going to say that this rotation, this angle d phi, is so small that this length is the same, even though like it's a you know what I mean? It looks like you got a right triangle where if this is your hypotenuse, it has to be bigger than the other side, the longest side. But we're going to say this angle is so small that this length AB prime is the same as length AB. Hell yeah. But that's the thing with textbooks. Just every little sentence is a very particular. It's important, and sometimes it's like, well, where are you getting? Cool. So those don't change during the small rotation. But now they're going to talk about the angle. However, the angles at the corner of the element are no longer equal to 90. The element is therefore in a state of pure shear. Oh, interesting. So yes, so this is your differential element A, B, C, D, and that's the other thing that I guess from my drawing, I'm going to take like this differential element dx is 2 molecules in width. And the box that I'm going to draw is going to be 4 molecules. So there's a molecule, there's a molecule. I'm just stretching them out to fill this rectangle. But we've talked about how, hell yeah, we have a rectangle of 4 iron molecules. Even though they're just calling this an element, they don't get into the number of molecules. Because it's a differential element, it doesn't really have to have numbers. I mean, it could be a fraction of a fraction of a fraction because it gets infinitesimally small. That's the other thing I do not like about visualizing infinitesimally small things. But hell yeah, so that element is in pure shear. And they don't do a very good job because they kind of make this a long rectangle. It probably would have been better if they kind of made it more of a square and made this ABC, look like a diamond shape to represent just a nice shear. Hell yeah. Hell yeah. All right, moving on. So booyah. So we're finally done with that little section of wording, and now we're going to move down here. So this says, which means that the element is subjected to shear strains, but no normal strains. All right, cool. So we're seeing that there's shear. You have an element was rectangular, and now it didn't lengthen. So AB prime is not lengthening appreciably, even though visually you can see that it lengthens, but they're going to say that lengthening is negligible. And so there is no longitudinal strain, axial strain. There's no lengthening of the bar. And so the only deformation is a change in angle, which we represent by shear. So cool. And so the magnitude, and so it says go back and review shear, which in this book, man, the sections, this is a very good chapter because it reintroduces this concept of shear in a very useful way. But in this gear book, Material Mechanics Gear, the writing of shear is in chapter 1, chapter 3, it's kind of spread out throughout the book, I feel. Okay, hell yeah. So the magnitude of the shear strain at the outer surface of the bar is denoted by that angle. So, and that's going to be, how do you say that? Something max. I don't know why I'm spacing on that little letter. Gamma? Is that right? Yeah, gamma. I'm just going to say gamma. So gamma max is equal to the decrease in the angle at point A. Now I'm spacing out. The magnitude of the shear strain on the outer surface of the bar is an angle. It's measured in radians or degrees, who cares, is equal to the decrease in the angle at point A. The decrease in angle at point A. What the hell are they talking about? That is the decrease in angle. Oh, there you go. BAD. So let's do this. So we have BAD. This is 90. Oh, hell yeah. And we get an decrease of that. So that's the other thing, is if we have a box like this and now we're going to go like this, we have a clockwise rotation, we have positive shear. Positive shear means that this corner of the box decreased in angle, and then this corner of the box increased in angle. So you do you. But hell yeah. So that angle decreases. They just wanted to say that. And from this figure, 3, 4b, we see that the decrease in this angle, this decrease Yeah. So the decrease is this angle. So whatever this angle forms, this angle gets decreased because this used to be 90. Now it's 90 minus this angle, and so that decrease is that minus. So that's that, and I'm going to do this from radians times radius is equal to arc length. So check this out. So we have this is the angle. So we have radians, that's our radians. Radians times radius. So this is our radius. So here's our angle, here's our radius. That has to equal this arc length. So hell yeah. So even though it's on this another curved surface, like, hey, this is a straight line. I'm going to rotate this straight line to here. That's my angle. I could rotate this straight line around point A. So that's what it would look like. I think this is very good. You know what I mean? So the angle could have rotated out there. And this arc length, we could have rotated this angle 360. That's not in the domain of this because this angle has to be really small. But if we did rotate it 360, we rotated it its circumference, which is 2 pi r. Sweet. We only rotated it a little bit. And so because this is so tiny, we use the fact that if this angle is measured in radians, and the radians are small, we get this nice radians times radius. So you have like angle in radians times radius is arc length. This is the one kind of I represent. And then it sucks. I don't like this. Is this gamma? I think it's gamma. The fact that the angle is gamma. I don't think this is a very angly Greek letter. You know what I mean? I've actually never have looked at this Greek letter and thought, oh, hell yeah, that's an angle. And that messes with me. Because if I don't, like, I think I'm just used to that being an angle. And I'm for sure, I'm okay with that being an angle. I'm okay with, like, the capital of this being the angle. At no point in my college career did I ever feel super confident that I'm just like, oh, hell yeah, that's an angle. And that sucks, man, because that's fundamental. If I can't look at this letter and think angle, I don't know, that's like looking at velocity v, just a little v, and then just not having any clue what the hell that is. You know what I mean? You're just like, is that length? Yeah, that would be it'd be like, yeah, if I looked at the velocity v and just thought length with a question mark, that sucks. That's not going to help. And so, yeah, just the letter choice, the Greek letter choice, I don't know, I'd change the game. But anyway, so yeah, so now we have radians times radius is the arc length. See, this just doesn't look very good. But anyway, and then so we have this gamma times the radius is AB. And even calling this AB sucks, just with these two little letters representing the length. You know what I mean? You might want to throw a length over that. Even capitalize the letters, so then you almost have like a vectory looking thing. I don't know. I don't know what you're going to do. But it's just the absolute value of them. It's not a vector. It's just the length. So anyway. Yep. Okay, so hell yes. So you have angle times the radius is equal to the arc length. And that arc length is b to b prime, just for now. And we're going to use that same formula again. Hey, look at this. I know the radius. The radius times d, so we have the angle. This angle is d phi. So we have the angle in radians. Radians times the radius. In this case, the radius is just r. And that's kind of what, and then this is the arc length, is equal to b prime. Okay, hell yeah. So one equation says this is equal to b prime. And then this says this is equal to b prime. So hell yeah. So they're just doing it all in one step, and I think that's too much. So we're going to say this gamma AB is equal to d phi r. And now we're going to solve for gamma. So we have gamma is equal to... Oh, bummer, dude. Did they... never mind. No, they just did one step at a time. I'm doing 2 steps at a time. But hell yeah. So this was the first step. This is the first step. So there you go. So we already did that. Radians times radius is arc length. And we're just solving for the angle. So we're just getting AB downstairs. So that's what they have here. But again, you have the same thing over here. And we could say that B prime B over here is D phi R. So we could throw this change in the angle R upstairs, and we're going to see what they do. So hell yeah, let's just keep reading. And so hell yeah, see this B prime, it's R d theta. Hell yeah. And then length AB, they're going to say is just, well, that's just the derivative of dx. So hell yeah, so there you go. And I'm just kind of reviewing this. I kind of reviewed this probably like 3 months ago. I'm doing no prep on this. I'm just kind of reading it cold, but still I'm intuiting, like I've already done this material, but this is very helpful for going into new material, because to just even look at this equation, they're going to say, hey, this angle is this length divided by that length. Okay, I have this divided by that. So I don't know. I mean, this divided by that, it seems like the tangent. But yeah, you have to go small angle, radians times radius. So they don't spell out that whole radius times radius. And even just going from reading this paragraph and then jumping into this equation, you're like, well, now I'm lost. You know what I mean? And now this picture, I don't see how they got there. And that is with these small angles. I would go back and not have small angles. You know what I mean? So if I actually wanted to solve for this, I would say tangent of gamma is equal to this. So if I had tangent right here of gamma, that's opposite over adjacent. So here's my 90. This is my angle. This is the opposite. This is the adjacent. And so BB prime divided by AB. Then we just say that tangent of phi is the same thing as sine phi divided by cosine phi. And if the angle is super small, cosine of 0 is 1. And sine of a tiny, tiny number, it seems like it's 0, but it's still going to have some value. And let's look at a right triangle. So here's kind of like a right triangle. That's a fairly small angle. The sine component's going to be that. The cosine component's going to be that. And what we're comparing it to is this. I hate the unit triangle, so make it 100. Because now you're saying that this is 100%. Still represents 1. Hey, look at this. We're going to divvy it in half. Okay, hey, this looks like 50%. Hey, this looks like 95%. So now what we're going to do is make that hella small angle. So I'm going to come in like here, take a small little slice. Here's my 90. Now here's my 100%. Hey, look at this. It looks like 100%. But what happens with small angles, and let's do another one. Pen ran out of juice. There you go. Hey, still, this top one, hypotenuse is 100. The bottom one, pretty damn close to 100. They ain't changing, but look at this. Looks like we doubled that distance compared to that distance. So with small angles, your sine is still a significant value right away. Your cosine don't change. So that's where even a tangent of an angle, this cosine for sure just kind of goes away as a value of 1, but this sine of the angle just becomes the angle measured in radians. But you have to measure it in radians. I'm not going to, I'd spend another 10 minutes talking about radians. But I should. F. All right, so if you have a circle, here's your radius. Cut a string, drape that radius around the circle, you'll get to there. Definitionally, this is an angle that got swept out. The arc length is this distance r, but this angle that gets swept out we're going to call 1. 1 radian. Hell yeah. The arc length is radians times radius. And hell yeah. Yeah, 1. And how many of these strings can you go around a circle? There's 1 radius, there's 2, there's 3. You get 6 strings around 6.28. You get 2 pi of those all the way around the circle. So hell yeah. So you're gonna get 6.28. So you're gonna have 1 radian, 2, 3, 4, 5, 6, and then a 0.28 radians. So yeah, so the full, and then like a circumference is just radians times radius. So you're gonna have the angle times the radius. The angle is gonna be 2 pi, and then the radius is r. So hell yeah, circumference is 2 pi r. That just right there does not get explained enough, and that's where I'm just hesitant to even that's what I should do every time though. But it's exhausting because it feels like we've been cheated in our education, because no one doubles down and people just say radians, and then everyone knows that no one knows what a radian is. So you just got to keep repeating where radians comes from. Hell yeah. But then once we do that, then hell yeah, this is just the angle in radians, and tangent of this just becomes that. The cosine goes away, the sine part goes away, and you just have the angle is equal to, what we would have tangent to the angle, small angle, it's just the angle in radians is equal to that. Opposite over adjacent. Hell to the yeah. All right, we're getting our groove back, you know what I mean? I think this is very important for me. Just being able to talk through stuff. That's the moneymaker, honestly. I mean, the moneymaker is like doing things crispy, 5-8 minutes, blah, blah, blah. But I don't think so. I mean, this will keep me going forever if I just do me, and I'll keep improving. You know what I mean? And I think it's worth it. There's no lecture that you're going to learn. You're never going to learn anything from an 8-minute video. You're going to learn how to copy the information into the problem that you're doing. But that's it. You know what I mean? I think you really do need long hour, 2-hour, 3-hour lectures. And even lectures suck, because you need that lecturer to do the lecture and then go through 3 hours of problem set. For every 1 hour of lecture, you should see someone slow roll 3 hours of problems. And that's kind of what we're doing. And we'll get back into problem solving mode. But I just get, I don't know, I get bummed out that, sitting down with a problem and not solving it. You know what I mean? Just spending an hour and getting nowhere. But that's reality, and I think that is still worthwhile to show. All right, hell yeah. So there you go. So we used both of those radians times radius. This is the angle, radius, arc length. Here is an angle. We have a radius of our arc length. Both the arc lengths are the same, so we have 2 equations. We relate them. And when we do that, we get that. You do you. I'm not going to redo that again, but yeah, 1 equation. Radians times radius is this arc length. Other equation, radians times radius is this arc length. Put the 2 equations together. And we should just be able to do this mentally. AB angle is equal to R angle. So we have, and then AB is dx. So we have dx gamma is equal to d phi r. They're not going to write it like that at least once, but get this dx over here. Dx gamma is equal to d phi r. So we have gamma dx, radians times radius, is equal to radius times d phi. So there you go. If I got this dx right here, I would have radians, radius, and then this is radians. We'll get this d phi on that side. I like to, when I write things, because I have this radians times radius is arc length, kind of rhyme in my head. I don't know. It's just a good axiom. I always like to write the angle first, even though no textbook's going to do that. But It helps me. It helps me being like, hey, there's the angle. There's the radius. Radians times radius is arc length. And I just use that axiom of radians suck. Radians times radius is something normal. In this case, it's arc length. Radians per second times radius is something normal. That's tangential velocity. Radians per second, which is angular acceleration. So if you have radians, that type of radians per second times radius is tangential velocity. So you have this idea of radians times radius gets you something normal. I think it's a pretty good, hell yeah. All right, so this equation relates the shear strain at the outer surface of the bar to the angle of twist. And I don't even realize that this is an equation, you know what I mean? So what we have is we're applying some torque, we're getting that twist, and I think that's the first thing that's the easiest observation for things at a twist. Hey, this end over here, I'm going to twist this end. This end rotated one time. Cool. We have a length. I can figure out the angle. I know that this angle on this very end is 2 pi radians. You know, we just talked about what radians are, so might as well talk in radians, or it's 360 degrees. Halfway, it's going to be pi radians. Cool. If we take this little slice, both slices are going to basically rotate pi radians, but it rotates just a little bit more. And so, so let's take a look at that equation, because isn't it a differential equation? And I'm trying to get used to what the hell differential equations, almost swore. So we have d phi dx, yeah, that's a differential equation. That's the change in that angle when you change x is equal to, and multiply by the radius. So the radius times the rate of change. I don't know if you call it rate of change. Does rate of change mean time where you're independent variable? But this independent variable is changing your distance. So you have the change in the angle when changing like along the bar, when you move along the bar, multiplied by the radius is equal to the max the max angle that's forming at that location. Oh, yeah, because that's the other thing. No, this is very important, and I'm just kind of picking this up. If we have these 4 molecules, we know that they are shearing, and so we don't want to kill people. We can only have this angle be so much. You know what I mean? It's going to be 0.004 of whatever length this is. You know what I mean? It's going to be 4 radians. I mean, I'm sorry. If I said 4 radians, sorry about that. It's 0.004. Steel is 0.002. That's going to be the change in length divided by the length. No, I was right, because I said this distance was 1,000 meters, and then, yes, this length could lengthen by 4 millimeters, which gives you an angle in radians of 0.004. And since we just covered how you can ditch the sine and tangents, because it's just the radians. Look at this. This angle in radians times radius is arc length. Arc length is 4. 1,000 times this angle. 1,000 times the angle is 4. So 4 divided by 1,000 is 0.004. That's the angle in radians. Hell yeah. But it's because it's because of this differential angle forms, and I think I'm just going to go out on a limb that this happens at every cross section along here. You're going to get the same shear max. This is a constant value. This value is not a function of the distance x. It's just a function of the rate of twist. Yeah, I'm getting better at the math. You know, where you're just like, well, if this is a function, gamma max is proportional to the radius, and then the chain, this dx dx, but it's not. It's not a function. It's not rx. It's not rx d phi dx. You know what I mean, or anything like that. It's not a function of x. It's a function of the radius and the rate, I think you would call it, I don't know, just the derivative of phi with respect to x. The change in phi when changing in a small distance x. Even when you say it correctly, it doesn't register that you're learning anything. Damn it. All right, so this equation relates the shear strain at the outer surface of the bar to the angle of twist. The quantity d phi dx is the rate of change of the angle of twist. And so, yeah, so there you go. So we're going to go back to, like, what the hell is rate of change? I don't know. But check it out. Right here, the angle is 0. Right here, the angle is phi. The change in length is L. Right here, we're going to go L divided by 2. So if we go halfway, we got L divided by 2. What's this angle? Well, it's going to be phi divided by 2. Okay, hell yeah. So now we're kind of understanding what this rate is. If we and it's constant. That's a linear change. Over here, this angle changed from over here. The angle is 0. Over here, it's phi. Halfway, it's phi divided by 2. A quarter of the way, it's phi divided by 4. So as we move from dx to 2dx, the angle just doubles. It doesn't do anything with the square or anything like that. So we just have a so the angle goes from, and then again, the angle goes from 0 to 1 with a small little change, and then it goes 0 to 2. The rate of change is like the angle was 0, and now we have a little bit of angle 1, and now we have a little bit of angle 2. So the change in the angle is 1. So we have a value of 1. The change in x, we're going to say x is 0 to 1 to 2. The change in x is also 1. Cool. And again, this is your independent variable. This could be 2, 4, 6. You know what I mean? There you go. So this is now 2 divided by 1, and we get a value of 2. This value will always be just a constant number as we move along this distance, as we move x from 0 to L. Hell yeah. Alrighty. So yeah, that's the stuff that I'm trying to get better at. And textbooks, I mean, it's too gospel truthy where you're just like, man, just explain a little bit more. I mean, dumb it down a lot, you know what I mean? So hell yeah. So there you go. So they're going to say that rate of twist is probably a constant. I don't know when they get to telling you it's a constant. But the quantity, d phi dx, is the rate of change of the angle of twist. Remember, the angle of twist was a function of x. So they should have this little function of x. They shouldn't have got rid of that. With respect to the distance x. I guess they're just saying it. And then they should have put a comma and then write it again. That would have been nice. Cool. X measured along the axis of the bar. We will denote d phi divided by dx, the change in phi divided by the change in x, by the symbol. And now this sucks. And now they're just going to say, hey, this is the rate of change of the angle with respect. This is an angle in radians. That's going to be the units up top, divided by a distance in meters. So you're going to have inverse meters, and you're going to call that theta. I hate that, man. You know what I mean? I can't even see that this is an angle. And now you're going to use the angle that I always associate with an angle, and you're going to have it have units of inverse meters. Get out of town. All right, so, and it refers to it as the rate of twist. It's a differential equation. And they do use the word rate. Rate doesn't have to mean time at all. Okay, hell yeah. I was just kind of worried about that. All right, rate of twist, or the angle of twist per unit length. With this notation, we can now write the equation for the shear strain at the outer surface as follows. This should be good, because now I'm not following. Okay, hell yeah. Well, let's just go back to this. So we're going to say, hey, look at this. So we're going to have gamma max. The maximum angle is r, this little thing, r angle. But it's not an angle. It's a rate of twist. So this is twist rate, also called rate of twist, or it's the angle of twist per unit length. And I guess I'm just going to have to get used to that. You know, just red flags everywhere I see that. That is the rate of twist. And this is the equation that we get. Cool. So for convenience, we discuss a bar in pure torsion when deriving equations 3.1 and 3.2. This is equation 3.2. This is equation 3.1. Cool. What? For convenience, we discussed a bar in pure torsion when deriving these. Yeah, pure torsion. However, both equations are valid in more general cases of torsion, such as when the rate of twist is not constant, but varies with the distance x. Okay, cool. Because now we can just use our calculus. So, shame on me for thinking that this rate of twist had to be a constant. It could. So now we have this, so now we have this variable. Now I'm getting better at this. It could be a function of x. You know what I mean? So there you go. In our case, it's going to be a constant. So that's when it's not constant, but does vary as a function of x. In the special case of pure torsion, the rate of twist is equal to the total angle of twist divided by the length. Yeah, and so that's what we spent our time talking about. Ah, damn it. Whoa. Yeah, so back here, so we said we put a torque on this. This face moved an angle phi, and then we want that twist rate, which is the change in angle when we change length. If we're over here, no change in angle. If we're over here, we have this change in angle. And then when we're right here, we move only L divided by 2, but we only have phi divided by 2. So the change from here to there is phi divided by 2 divided by L divided by 2. So that's phi divided by L. And I can't call this phi. That's really difficult for me. It feels like, how I don't know. It seems like I'm saying two syllables when I say phi. Maybe I'm just not used to it. But phi seems like I'm saying just like a half a syllable, or it just seems easier. I don't know if it's just because I'm just used to calling it phi. I'm just going to call this phi. I've always called it phi. I'll try to call it phi, but whatever. Sometimes you got to psych your brain out. All right, sweet. So hell yeah. And then that twist rate, I'm getting better at that, is phi. Did I say it right? That's weird. Phi divided by L. Hell yeah. So the twist rate, theta, is phi divided by L. Just know that theta is in units of radians per meter, which is basically inverse meters. Therefore, for pure torsion only, this angle that forms is this equation, the radius times that twist rate, which if we throw back in the radians times radius type thing, this is going to be d phi dx, because again we had that gamma dx, angle radians times radius, and then over here we had d phi, which is radians times radius. So I think I can remember this equation just from the radians times radius is arc length. And then I'm going to have that equal to the same arc length forms right here is equal to the radians times radius. And then we just say that d phi dx is this value twist rate, and which we took that radius over here dx and we brought it over there. So hell yeah. So this is the equation for the max, and this angle, this is the maximum. We know this angle from the material properties. And so if I know this value can only be, like, I'm just going to throw a big number in there. So I'm going to throw that 0.004 for steel. And then I know my radius. I know my length. What do I know? I know my twist I know my angle of twist for steel. Now that is fascinating. Is that how this equation works? Doesn't seem like that's how it works. Wow. I don't think I... Hopefully, yeah, I'll have to double check that one. But, I mean, that's what the equation said. This is your... yeah, because you're going to have... if I put this max, well, this is a function of x. I don't know. But let's move on. All right, this equation can be obtained directly from the geometry of that first figure by noting that the angle max is the angle between the lines PQ and PQ prime. That is, that angle max is the angle QP Q prime. So yeah, let's go back over there because that is fascinating. So we have this. This is our max angle. Oh yeah, because they're gonna say that. Yeah, so this angle is equal. They're gonna say that is what? Are they gonna say that is equal to? I don't think so. I think they're gonna use radians. Let's do radians times radius here. So this is our radian. Or this angle is phi. That's radians. Our radius is L. So we have phi L is equal to radius times radians times radius. This angle, I'm sorry. Oh, hell yeah. Okay, there, yeah, this angle right here, they don't write that in. Okay, so yeah, that's fascinating. I didn't even see that. This angle right here is phi max. Because this angle is always the same. Now, is that true? Because this angle is 0, and then this angle is phi. You know, I definitely see that. But if I take a little differential slice right here, we get, you know, and I can even take this slice like right here and say that this line moves down to here, and then so we have our diagonal that formed. And then so this angle right there is that phi max. And it's the same thing because the rate of twist is constant. You know, it's like saying this whole thing is just 4 long iron molecules, and then we get that they used to be square and now they're angled, and we get that angle to form, and that's our shear. What do you call this angle? Shear strain. Yeah, the angle that forms in radians is called shear. Is that even true? Shear strain? Shear strain is the angle that gets formed. I think that's how, yeah. And because it's dimensionless, and as well as epsilon, shear strain, normal strain is also dimensionless, but it's a change in length divided by total length. Where this, I think, is also kind of a change in length divided by total length. Let's talk about that. Because if we have radians, that's going to be this, times this radius, that's meters, is equal to this in meters, then this times this is equal to this. So get this by itself, that's meters divided by meters, which is dimensionless. So yes, this shear strain can also be like meters divided by meters when you do the small angle theorem. And so that's kind of fascinating. So it is very similar to the units on normal strain. But hell yeah, I did not realize that. But yeah, this max angle is always the same. And so if you twist this side and measure this, that is not the max shear angle. Like you could twist this 3 or 4 times. You know, so this angle could be 22 radians. You know, it could be just, you know, 6. You divide this by 6 and you get the number of rotations. You should always do that. You should know that 6 radians is a circle, basically. You know what I mean? But yeah, you could rotate this 6 radians. Anyway, you could rotate it 6.28 and then keep going. This could be 6.5, or you could have already rotated this one full rotation, and then this line is going to do. Oh man, is that true? Oh yeah. But from the picture, like let's say we lengthen this twice as much. There you go. I think this is a better way to do it. Because if we lengthen this photo twice as much, this angle keeps going. So now we have 2L, and then this angle moved like this. This angle, maybe it moved 30 degrees. Hey, this now moves 60 degrees. Cool. Okay. So if we keep lengthening this bar, we would be able to rotate the whole thing a full circle. This angle would helix around, and this angle would still represent the max shear. So that's where I didn't want to get confused by having the same picture, very short, rotated a full 360, where this, this thing rotates, this like this actually does helix all the way around. And how would you draw that? You would say it helix down and back up, and then down and there, or something like that. Cool. All right, so let's go back to that equation. Because it says, yeah, this max shear is this equation, R feet. And it says, in the special case of pure torsion, the rate of twist, and that's where we got on that tangent. The rate of twist was this phi divided by L, and therefore you plug that in to this equation. So this is the general equation. And then you want to figure out what the rate of twist is. The rate of twist is the derivative. And this derivative, might be not constant. But in our case, it is a constant. It's just phi divided by L. That's this twist rate. And then so we throw that in. So we're going to have R phi divided by L. And that's what we have here. R phi divided by L is gamma max. And cool. So this equation can be obtained directly from geometry. And now, and then so if I throw in this value of 0.004 radians, and I know my radius and I know my length, I can know how much I can twist a chunk of steel. I think that's the first one to do, to be like, hey, we just derived an equation. Like, go test that. Go get some sort of chunk of steel, twist it, and then do the test where you twist it and then have it go back to its original shape, and then try to twist it right to the point where it doesn't go back to the original shape, and then see if that angle that you generated is 0.004. And it's pretty simple. We just talked about how if you have a 1 meter or 1,000 millimeters of bar, so like here's your bar, then your angle will be 0.004 radians, which means that your arc length can be 4 millimeters. Okay, so hell yeah. So let's say that we have a 1/4 inch steel. Let's say this is 1/4 inch diameter. So circumference is going to be 0.25 times 3. Let's just say we have a diameter of 1 inch, maybe 20 millimeters to 25 millimeters. I'm sorry, we have a circumference. So if our diameter is 0.25, we're gonna go to 0.75. That's gonna be our circumference, 0.75. We're just gonna say it's about 20 millimeters. So there you go. So right there, and what does 4 go into 20? That's 1/5. So now, like, that's the stuff. That's probably where we're going to end this video, because the next thing is we have to talk about, this is the max, but if we go inside the bar hey, that angle, see how this angle, like this angle don't change. The rate of twist right there, or this d phi don't change. But as we go inside the bar, hey, this gamma does. And if we take a little, cylinder inside of this, then yeah, this angle doesn't change. But this becomes much smaller. And yeah, because this becomes smaller, your Y max can there isn't the angle. Yeah, this angle that forms in the middle isn't hardly anything. So if you have a very slender piece of wire, you can just keep rotating it and then let go, and it does go back to the original shape. But yeah, this is a fascinating. So if I have a 1/4 inch diameter steel cylinder of steel that's 1 meter long, or 1,000 millimeters, has a circumference of about 20 millimeters, I can move this an arc length of 4 millimeters, which is 1/5. I can rotate that circle 1/5. So I'm going to break up a circle into about 5 pieces. And that was 6. 1, 2, 3, 4. Now it's 5. Sweet. So we broke up a circle in 5 pieces. That's about how much I could rotate a steel bar. And now I just know. Like, I have at least that in my head. I think it's very important anytime that you do a proof for material mechanics is, find something that you trust mentally, or something that you could actually experiment with. Because I could probably find, or even go to the steel yard to do that. That'd be a fascinating one. Weld this to a wall, and then just rotate it 1/5 of a turn, and then just get a feel for it. Does it feel like if I rotated it a little bit more, that it would permanently deform? And you can kind of feel that. You're just like, ooh, I'm kind of stretching it. All right, hell yeah. So hell yeah. Before we dive into the because I think that's kind of, once you dive inside, that kind of gets a little bit more complicated. So, but booyah, we did it. You know what I mean? But yeah, I think taking a fresh look at that last, now we better just, because now we're going into problems. I mean, if I can't just finish this, that would suck. So anyway, so shear strains within the bar. The shear strains within the interior of the bar can be found by the same method used to find the shear strains, gamma max, on the surface. This is the shear strain. They're saying what this term is, shear strain, which is angle in radians. Because radii, right there, rho, in the cross-section of the bar remains straight and undistorted during twisting, we see that the preceding discussion for an element A, B, C, D at the outer surface will also hold for this inner surface, maybe like A double prime, B, I don't know, whatever you're going to call it, on the inner surface. So we also hold for a similar element situation on the surface of, sorry, I'm just reading this again, but on the interior cylinder, we could do that rectangle. And that rectangle is going to form that angle, and that means shear. We talked about that square becoming a diamond, becoming shear, that requiring a force, that force being a distance away from the center. That's a moment that can withstand the torque. Cool. Sorry just to blow through that, but it's good to reiterate that kind of stuff. Yeah, interior. And that radius is going to be rho. So that's typically what happens, is you have the R is going to be denoted for the total radius of the cylinder. If we have to denote, they should just say R of X. I don't know how, if this is length, yeah, I guess they just do it with rho. So that's rho. So rho of, that's weird that you don't have like a, anyway, like if this variable is X, like wouldn't this variable be R? I don't, whatever. But anyway, so you have rho. Thus, interior elements are also in pure shear. So just know that rho varies. Rho varies as you make this cylinder tiny to the outer cylinder. You know what I mean? So rho varies from 0 to r. Just like x varies from 0 to L. No, I get it. X is just a variable that goes from 0 to L. R is just a... no, you're saying this rho. Rho is that variable. Rho is the variable that varies from 0 to r. Cool. Just like x is the variable that varies from 0 to L. I'm glad I'm saying that correctly because that helps my mathematics. All right. So thus, interior elements are also in pure shear because we can draw that little square with the corresponding shear strains given by the equation. And you could do that same thing. You could say that this is dx and this is gamma. So radians, gamma, radians times radius is this arc length, which is equal to radius times radians. Radians times radius equal that arc length. So we have dx gamma is, if we're saying radians first, radians times radius, it would be gamma dx is equal to d phi rho. No one says it that way, so we have dx gamma and then rho d phi. So we have, and if we want to solve for this, we're going to have, get this on the other side. So we would have d phi dx times rho. And d phi dx is that theta. So they're not going to spell it out for you. They're just going to go right to this. So we have gamma is equal to rho theta. But that's a lot. You can't just mentally go to this without actually doing the... it'd be... I can't. I have to do that radians times radius type thing. Now, do I? Well, maybe I can simplify it. The multiplication of this and that is equal to the multiplication of this and that. I can kind of see that. And then therefore, if I have to get this by itself, I get this downstairs, and that is that twist rate, which is theta. So yeah, that was a little faster. So theta rho. Because that's the other thing. It's good to be like, on a stranded island and be able to do the proofs without a textbook. But then once you have gone over it, just like playing the piano or something, it's like just get there faster. Like what's the deal? Like why can't you see it in a faster way? I need to work on that. So yeah, so I see that. So gamma, so I can do it real fast. Gamma is equal to, get this to the other side, so it's those two things, which is twist rate times rho. Hell yeah. And now what are they doing on me? And they're saying that, what did they do? And they're saying that the twist rate, because the twist rate is, so over here we have twist rate, so we have the max angle that can form is the radius times the twist rate. I totally even forgot about this equation. I would have to, let's do that. So we have this angle and this length, so max times dx is equal to this angle times this length. So we're going to get this to the other side. That's d phi dx, which is the twist rate times the radius. So I can see that. So we have this max angle is the twist rate times the radius, such as this max angle is the twist rate times rho. Okay, and so if I know that, or just the angle at any point along here is the twist rate times rho. So they're going to combine both of those equations. They're going to say this is the twist rate rho theta, and this is max r theta. So let's solve for theta. That's going to be max divided by r, and that's what they put here. They're going to do max divided by r rho. So hell yeah. So now we have the measured radius divided by the total radius, which is just a proportion. If this is 0, then this becomes 0. And if rho is r, then we have 1, and this is max. And so we have a linear relationship, and that's what this shows. It's not an x squared, it's just a linear relationship. So if I'm at the center, this is 0, and if I'm at the surface, it's max. This equation shows that the shear strains in a circular bar vary linearly with the radial distance rho from the center, with the strain being 0 at the center and reaching a maximum value, shear max, at the outer surface. Hell yeah. And we have, you know what I mean. And then the next thing is bringing circular bars, just the linear elasticity of these, the fact that we apply a torque, we do get an angle to form, and we develop stresses. And then there's going to be, we'd have to go talk about the stress, and we do this from just knowing that we can get this angle in shear to be a maximum. And if we can get this to be a maximum, then we're going to get this shear stress to form on the surface, because this little square is, from our perspective, is just like one molecule. It's 4 molecules and it's only 1 molecule thick. Well, this whole cylinder is made up of a bunch of these layers, like an onion. And so one layer, 1 molecule thick, requires a force over that area of molecules, and that's going to be a stress, force times area. And then we know the stress on that molecule. Hell yeah. And the stress is a cool term, because it doesn't matter if this thing is a tiny chunk or a full band all the way around of molecules, like 2 disks of molecules on the surface, where the surface area is more, because that, again, if we had a hollow tube that was just 1 molecule thick, all of those molecules would have to take the torque, and so yeah, so there you go. So it's kind of fascinating how stress, I'm getting more used to it, but stress is irrelevant. This value of stress at the perimeter is going to be the same all the way around. The stress times the area of those molecules is what's holding back that torque. Now, if this is a solid sphere, then we get this relationship, and then each of these layers holds back this torque a little bit. But mainly the outside holds back the torque more, even though this is a linear shape. The area, look at this, because it's this value times the area also grows non-linearly. You know what I mean? So that's where, hell yeah, and that'll be for the other videos. But hell yeah, so we'll just go over what this says of circular tubes. A review of the preceding discussion will show that the equations for shear strains apply to circular tubes, as well as to solid circular bars. So this angle max is always going to be max, and it's pretending like you do have material at the beginning. And that's the same thing as, like, you know what I mean, making this and then throwing this, and then here's your square of 4 molecules. You can only shear them so much. Cool. And this shear is the max, and what we just derived is that if we take a small little cylinder in the middle, that angle just so this is the max on the perimeter. If we go all the way to the center, that's 0. And then if we go halfway, half the radius, hey, our angle is half. And so if we just made the material, if we just made the bar just half a bar, well, yeah, then we can actually twist it more. So that's kind of the maybe counterintuitive, but hell yeah, like a big round, a big cylinder that's thick, you can't twist as much compared to a thin wire. See, it's kind of counterintuitive when you're just like, well, why can't you twist? It's bigger and stuff. But there you go. Hell yeah. And this shows that, like this angle can only be so much. We just showed that if we go halfway, well, we're only moving at half. And then so, hey, you can move this one more. but not if it's connected to a bigger. So you can make this cylinder here and then actually have a max twist that's double. But the second there's an interesting question in material mechanics that does this. Hey, you have a bridge that takes some bending, and you're going to put a load on it that can withstand the bending. But then you're going to weld a thin sheet of steel to it. And guess what happens to this steel? It rips apart. Like, let's say this steel compared to this honkin' bridge, just from geometry, you know what I mean? Like this is the angle that gets formed. If you took this way out here, then that's synonymous. If you have a thin bridge that can be very flexible, cool, it's plenty strong and it can do its thing. But then if you take that same bridge that's very flexible and decide to weld, that's a very fascinating engineering question. Because now you're going to take that same very flexible bridge, so this is before it's being flexed, and then you're going to weld a thin piece of steel, which is plenty strong. It's just really thin, and you're going to weld it to this underneath this bridge. And then just say this steel is so thin it really doesn't even help with the bending. So we're going to go from this shape still to this shape. Say this thin steel really doesn't help resist any of the bend. It would though, but I mean if it's so thin it won't. And then so that this is connected right there at a 90. This is connected right there at a 90. This is connected there at a 90. This is connected there at a 90. Holy hell. This length don't change, you know what I mean? Because it's welded, so this length, well, bear with me on that. But just pretend like that length doesn't change because it's still very close to the center. So, because this is a very thin but strong beam. But hell yeah, this for sure changes and it just rips apart. So, hell yeah. The other thing I thought would be cool on that one is if you just had a huge bridge and you were able to, or just any normal bridge, and you were able to kind of weld two chunks of steel, it'd be like a little finger death trap. But then as a car went over it, these pieces of steel would separate, and that would be fascinating. You know what I mean? Because you just think a rigid structure is rigid. But then these two chunks of steel would separate, and then you could go throw a walnut in the middle and crack it. So as the car's rolling over the bridge, it opens up, you throw the walnut in, it cracks, crushes, don't get your finger cut in. You got to wait for the other car, and then it'll drop your little walnut dust. Hell yeah. All right, so we are thoroughly done with this. But yeah, we're back, I guess, but I have a hard time just wanting to do like a 3-minute problem. I want to do this, but this turned out to be probably 2.5 hours, and I just can't do that every night. Maybe I could, though. But hell yeah. And it is good for me to just keep doing it and going through like all the steps to get a little bit better. And but for sure. So we did it. For the next video, yeah, you got to bring in stress, those terms, and talk about that, and then you got the full picture. And then you can talk about how, the forces, I don't know, max stress and stuff. Yeah, it's important, somehow. And looks complicated. All right, we're going to be done. This was Torsion. So thanks for joining me. Hell yeah.